Hi guys, so in this video we're going to be continuing differentiation. So this is the introduction to differential calculus. Let's look at the next thing. So in the previous episode we covered limits. Now over here we're going to be covering something around first principle, which relates to limits. So let's say, so when we think about differentiation, we think about like the instantaneous rate of change almost. So let's take a look at something. Let's say we have a point here. Let's identify this as x, and then f of x. So essentially, when you have an equation, it's written in the form f of x equals mx plus c, or y equals mx plus c. But in this case, we can write as f of x. Now, let's say we have another point that's further down. Let's say it's over here. Or actually, let's put it over here. Let's say this point over here is x plus h, so it's moved by x. This much is h because the x value is moved by that much. And then therefore the y coordinate is f of x plus h. And let's say we wanted to find the gradient. So that would essentially cause a line. Oops, my drawing's not very straight. Cause a line between these 2 points. And we can actually find the gradient of this line using the gradient formula, which is y1 minus y2 over x1 minus x2. So let's say we can use the gradient formula f of x plus h. So this is our y1 minus f of x over, and then x1 is x plus h minus x, which simplifies to f of x plus h minus f of x over h. Okay, so now let's think about how this is applicable to differentiation at all. Well, we could drag this point down so it's closer and closer to the original point until, let me just draw it magnified now, until the point is so close it's about here, or it's so close that's actually right at that point. So the way we would express this is that as x tends towards 0, what's the gradient at that point? Well, you might be thinking, okay, so why don't we substitute h as 0 and then find the answer? Well, if you substitute h as 0, that just gives us f of x minus f of x over 0, which becomes, and f of x minus f of x is obviously 0, so 0 over 0, which is indeterminate value. And this is where limits come in. So if you want to find the gradient at that point, yes, we do need to make h tend towards 0, because then that way we're essentially just taking one point and creating a gradient out of it. Well, we only have 1 point, so we can't really use the gradient function just yet, or we can. This is where differentiation comes in. So we would write this as the limit of h tending towards 0 and f of x plus h minus f of x over h. So you see, we're actually still using the gradient formula. It's just we're using it with a point that is we're making 2 points that are actually the same point. And that's why we have to make h tend towards 0, because at that point where h is 0, there is actually no gradient. It's actually indeterminate. So by doing this, we actually create a determinate value. So how does this make sense? Well, this equation here is actually the whole prospect of differentiation. This is what actually creates the differentiated equation, which we can then use. It allows us to find tangents, normals, etc., and minima, maxima, all those different points. And if we differentiate the function using this idea of first principle, which is what this is called in the topic of this video, well, then we can differentiate functions and use those applications further. I'll explain more about applications in the next section. Let's first finish actually understanding differentiation and how to do it. So basically, the pace of differentiation is finding the tangent or the change at that specific point. Okay, so we've established our first principle, which is the base of differentiation, which we would write as the limit of h tending towards 0 is f of x plus h minus f of x over h. And the way it uses limits, of course, is that we can't actually put h into this. We can't put h as 0 into this equation. We have to find a very, very approximate value of that. because otherwise we'll get an indeterminate expression, which is when it's 0 over 0, and you actually can't find the values of that expression. So now what we need to do is we need to actually show how this first principle works. Well, let's take the function x squared. So of course, we would write that as f of x equals x squared. So the other way we could write it, if we were putting in f of x plus h, we write this as f of x plus h. And we know that for every x plus h, that's put into the actual equation. So in this case, x is put in here. In this case, it would be x plus h squared. So for any x value, it would be replaced by x plus h essentially. And I think we covered more of that in the functions unit. I haven't started releasing videos on the functions unit, and I will do so soon. So now that we know what f of x plus h is and what f of x is, we can actually simplify. That would become x plus h squared minus x squared over h. Now we know how to expand binomials, so x plus h squared would just become x squared plus 2xh plus h squared minus x squared over h. We can simplify this down to get, well, the x squares actually cancel out, so we can already get rid of those. So it gives us 2xh plus h squared over h. And now we can actually factor the h in the numerator expression. Let me just get rid of the arrow. Which would give us h multiplied by 2x plus h over h. And what we can do now is we can cross these out. And that gets rid of our zero denominator, because if we substitute h in there, it would have a denominator of 0, which gives us 2x plus h. And now the brilliant thing is that we can actually substitute h as 0 now to get rid of h and only leave in x. So it becomes 2x. So x squared differentiated using first principle is 2x. And essentially that says that if you substitute like a value of x, for example, if we have this, any value of x, for example, x is 1, it will tell you the rate of change at that point. So when x is 1, substitute it back into this, which gives us a rate of change of 2. Or a gradient of 2 if we were to draw a tangent like that. But more on that in the tangents and normal section of the video. Okay, so let's try one more example to show the first principle, how it works. So let's say that f of x is equal to x cubed minus 3. Then we know that f of x plus h is equal to, and then we substitute x plus h into all the x values, it's x plus h cubed. Since there's only one x value, it's only that, minus 3. Okay, now we're ready to go. So let's substitute f of x plus h into our equation, giving us x plus h cubed minus 3, and then subtract it from f of x, which is just x cubed minus 3. We'll put that in brackets, x cubed minus 3. And then we divide it by h. Oops, that's a bad h. Which gives us, and then we can use binomial theorem knowledge to expand this. I'm just going to do it quickly. I'm not going to really show the steps, but you could use it more slowly. And then you subtract it. Okay, I'm going to go into the next line because, oh no, actually I can stay on this line. And then you subtract it from x cubed. But since there's a negative over here and a negative over here, it becomes a positive. So you add 3 instead. And it's divided by h. Okay, now you can actually cross some things out here. The x cubed crosses out with that here, and the negative 3 crosses out with the positive 3 over there. So we're left with 3x squared plus, oh, sorry, not 3x squared, 3x squared h plus 3h squared x plus h squared divided by h. And of course, we can factor out the h to get h times 3x squared plus 3hx plus h squared over h. And we can cross the h's out to get 3x squared plus 3hx plus h squared. And at this point, we can substitute h as 0 back into the thing, which would give us, this would become 0 because, oops, this would become 0 because anything multiplied by 0 becomes 0. This would also become 0 because 0 to the power 2 is 0. So our final thing is 3x squared. So when you have the equation x cubed minus 3, it becomes 3x squared. So that's essentially how you use first principle. It is actually the base of differentiation, because if you put any equation here and you put it through first principle, it'll give you the differentiated expression. However, in the next following videos in the introduction to differential calculus, we'll go over how to differentiate other things very, very easily. Because first principle, it's a very long method. While it is always correct and it will never give you the wrong thing, like if you were to differentiate x cubed minus 3, you would actually get 3x squared. There are many quicker, much more efficient ways you can use, like especially in the exam. It's very rare will they ask you to use first principle, but sometimes they may ask you specifically to use first principle. In this case, you would write it like that. If you are using first principle, also note that you should always keep putting the limit in until you don't need it. So use it, put it in here, here, but not here, because you don't need the limit anymore. Well, no, you do need the limit still. So put it for that one too. Put it for all of them until you've crossed out the h's. So don't put it for this one. This one here, the answer, you don't need the limit. But essentially, it just shows that you're substituting h in as 0 when you can. When there's a denominator of h, obviously the limit shows that you can't put in 0 at that moment. But other than that, I think if you don't put in the limit, you might get deducted. So make sure you put in the limit notation, which I've written over here. Anyway, so that's it for this video. I won't put in any worksheets because this isn't actually like a strict way of doing differentiation. But I will put more videos up on how to differentiate very efficiently, and then I'll put worksheets on for you to practice if you need it. But other than that, I think that's it for this video, and see you in the next one.